Welcome back to another HVAC-Engineering-Techie training video. Today's lesson is C-7, which is another lesson in our control training series. It's hot water central plant control system sequences. So this is going to take a standard sequence, high-level English language sequence, and break it down into component parts, clear down into reset sequences, and how those actually function. Remember, this is the channel that talks all things HVAC, all the way from design, all the way to efficiency and performance, and everything in between. So don't forget to become a subscribing member if you're not already. Just hit the subscribe button down below. Give me a thumbs up if you like the video. Cost you nothing, no one will bug you, but it's really important to me because Google uses that to value my videos, which actually keeps me on the air. So I'd really appreciate it if you do that. All right, let's get started in the hot water central plant sequences. Thanks. So now we're going to go over a list of our videos. I know you may have already seen this, but we'll go over it quickly. C1 is our basic system controls. C2 is DDC controllers and network devices. So you see the different kinds of controllers. DDC control architecture sees the layouts of the networks. C4, control components and devices. C5, wiring and installation, how you actually install all this stuff. C6, water-cooled central plant sequences. C7, which we're talking today, is the hot water central plant. C8, chill water central plant. C9, constant volume air handler sequences. C10 is VAV air handler sequences. C11 is outside air sequences. Now, all these sequent ones are designed to go much deeper than we've gone in the past videos to just a high level. These go into detail of exactly how they should program to work successfully. So hopefully you get something out of these. C12 is tuning loops, which is very important. C13, how to select and size control valves. C14, how to select and size control dampers. C15, how pneumatic controls work. So all of these are important for a well-rounded education of controls. I hope you get time to go through them. So I always tell an engineer, if you're going to do that, then you need to put enough money in your contract to be able to train all those people downstream of exactly how this is supposed to work and why you did it this way. If you're not willing to do that, then you probably will not have a successful project. That sequence will probably not get implemented, or at least not implemented correctly. Incorrect logic or logic components. Unfortunately, being a programmer is a little bit different, and if people, they don't actually write in English language, they write in the language of the special syntaxes, and the engineers probably have never been through that, so they don't understand those sequences, so they forget a lot of things. The sequence they write is in plain English. Say, I want this thing to maintain this temperature, but the control programmer has to do a lot of other things that you haven't thought about. He has to have entrance locations, he has to exit conditions, he needs to have timers, he needs to have all kinds of reset timers, and those things the engineer never thinks about, and it can lead to problems. So you may think it's really simple. A lot of things that both programmers forget also, especially we fought it for many, many years, when you have a temperature reset and a pressure reset on a chill water system or a hot water system. People forget they're actually connected together by physics. So, if you increase the amount of flow, you don't need as much temperature difference. If you increase the temperature difference, you don't need as much flow, and they're connected. And that can lead to real problems if you haven't thought about the conditions of that physics changing what you're doing. And that's why Guideline 36 has become relevant, to try to prevent those problems, and to prevent those problems where they basically get wind up. You do a sequence you think is really cool, and you come back the next morning and the temperature difference is as great as it can be and the pressure as high as it can be, and you go, what the heck? Or vice versa. So you have to kind of program it to make it do what you want it to do. Remember, they are connected. Too complex for successful implementation. I've seen some young engineers do sequences that are so complicated they can't hardly ever be written. I mean, I've seen it where they have like 5 or 6 different ranges for a reset. How do you do that? I mean, it's 2 is hard. 4 or 5 is impossible, and it's not necessary. So that's kind of something we look at. So control submittals are supposed to include a rewritten sequence that includes all details required to produce the desired sequence, or supply a manufactured standard sequence that has been fully vetted for actual performance. But unfortunately, what actually happens 99% of the time is a control contractor simply cuts and pastes the engineer's English language sequence into his submittal. So now we still don't know what he's going to program, because he's saying he's going to program exactly what the engineer wants, and that's a lie, because that's written in plain English. We need to see, as a commissioner, I need to see the actual sequence that he's going to program, so when I test it, I know I'm not writing a test that he can't pass. I need to know what his timers are. I need to know what his exits are. I need to know all those things to write a successful test. But they don't understand that, so they try to and the reason they do this cut and paste is they're afraid the engineers are going to disapprove their submittal if they don't do it that way. And then actually it's not the way it's intended to do, so we always have to ask for them to do it again. Control sequence standards, components for central plants, hot water central plants. There's an operating schedule, occupied schedule, conditions for start time, end time. Unoccupied schedule, when is that? Space environmental set points for occupied and unoccupied. If that space is directly into the system, it might not be. It might be on an air handler system. Room set point dead bands. And this is the standards if your room is involved. And that is cooling is 75 for occupied spaces. Heating is 70 for occupied spaces. Unoccupied is 90 and 60. And this is right out of guideline 36. I personally think 90 is too high. And the reason is for setback for unoccupied position, you want to make sure that temperature is not so great that the energy saved by going to that temperature is not exceeded by the cool down period. And I like to use 84, 85 degrees, right around in there. I think that's a good temperature for an unoccupied building. And when it needs to be occupied, it'll cool down quickly. It won't take an hour and a half to get down to temperature. But these are just ASHRAE Guideline 36 recommendations. No one have to follow, but that's what they can do. 60 for heating. And these are other rooms, operating rooms are always temperature sensitive, data computer rooms. Now they show 75 degrees across the board, but you might check that out, because nowadays data centers are in the process of raising their operating temperatures. They discovered, years ago, they thought that the servers needed to have 72 degree air, so we had pumped 68 degree air down into the room to try to keep 72, 73 degree air at the server, which means the exit of the server. Well, nowadays they realize their servers will run up to 95 degrees, so they don't need that cold of air. So 75 is probably reasonable, but you might be able to get away with being slightly higher. And then standard default water temperature set points for condenser water systems, which is cooling tower water, would be 85. 90 for unoccupied, and then during the winter time it'd be 75 and 65 if they're online. Chill water systems are 44 and 50 for unoccupied. Hot water is 130 and 90 for unoccupied. Those are the standard temperatures for water systems. All right, control sequence standard components: start stop, sequence condition for startup, sequence condition for shutdown, optimal start-stop conditions, optimal start conditions, optimal stop conditions. You notice I put a question mark on optimal start. We don't use stop much because what happens, optimal start basically the system remembers how long it took to get down to the set point temperature. And so when you say I need, I want it that people come to work at 6 a.m., so at 6 a.m. I need it at a set point, the system will automatically turn it on early enough to get to set point, and it will modify that as the season changes. So it's very good to start that way. It saves you a lot of energy. Stop, unfortunately, does the same thing, but at the end, so it knows how long it takes the system to get out of set point, so it'll stop the system early. And the problem with that is the building's still occupied, and you start shutting down HVAC systems, people notice right away, man, why did it just get quiet around here? We don't realize that HVAC systems put a lot of white noise into a building. So optimal stop just ends up getting a lot of complaints, so we just don't do optimal stop, but do start. Start's a good thing. Hot water supply temperature control sequence are both cooling and heating. Temperature control reset sequences. This is for hot water basically, so it won't have a cooling sequence, but it will have a temperature reset sequence. Hot water pressure control, this is a variable flow of your pumps. If you have that, supply a pressure control sequence. a reset sequence. Anytime you have a pressure control or temperature control, and if you want to be maximum on being high performance and saving energy, you will definitely need a reset logic on both of those. Operations data trends, what sense data and runtime, what does the operator need to see in the data trends, and operational alarms. These things should really be in the submittal, and the control contractor needs to do these and deliver them to the owner. Now, the specs all say that should be capable of, but if you don't do this, the operators may not actually know what they need. So you as a commissioner or you as a control person need to do them for them, because these are simple to do, but if they don't know, and they won't get used. And so what operating alarms? And a lot of times there's way too many operating alarms, so your job may be to limit them to the real important ones. Most important items for energy reduction: hot water set point maintained, hot water set point reset maintained. We have a big problem in the industry as far as maintaining energy, and that a lot of times, an operator has a responsibility to actually fix something. If a customer says, I'm uncomfortable, they expect him to take care of it. They don't expect any excuses. Well, I can't do that. I don't know how to do that. Or someone else has to do that. That's not what they want to hear. So there's a couple of easy ones that an operator is going to do to normally fix something. That's one, blow out a schedule. We'll let it run all night, and it'll be ready for you in the morning, I guarantee. Or two, well, it's that reset schedule. We'll just blow that reset schedule out of there, and you will be 74 all the time. It won't set up and down. That's a problem, because it will blow out your energy efficiency also. Loop tuning. All output loops fully commissioned and tuned. So tuning is a problem in that a lot of control techs either don't know how to do it, are not good at it, or just don't want to do it. And they'll give you all kinds of excuses. Oh, these are factory tuned loops, which is impossible. That's an impossibility. Two, these are self-tuning loops, and they may be, but they have to start tuned to be effective auto-tune. So none of those are excuses. The excuses are they just don't understand how to tune it, and you need to make sure they get tuned, because that's important for energy reduction. Occupancy schedules strictly maintained, that don't blow out a schedule. Operations committed to maintaining operations of the above. So persistence is really important in a building. You can build a building and set it up so it works perfectly, and an operator that doesn't know what he's doing or is not diligent can bring it to its knees almost immediately. So that's important that the operators understand what their job is and that they keep these things like they're supposed to be. So first we'll touch on radiant heating and cooling, because I don't know where else to put it. So radiant heating is where you have water tubes in the slab, the floor of the building. You could also have them in walls and ceilings, but normally they're in floors. And what happens is you bring warm water in at night and you charge the slabs, so when they get to work in the morning, the slabs are, if it's a residential type thing, of a hotel or something, that the floors are warm in the morning. And then this mass, what makes these really efficient is the mass keeps the heat and then slowly releases it during the day, which is very, very good. And then you can have radiant cooling also for the same, and you can put the same, you could use the same tubes, but unfortunately we don't normally do that, because for radiant cooling we have to keep the water 1 degree above dew point so we don't condense on the slab. And these are also popular to put in ceilings. We don't want raining, so what we do is we put a temperature control loop in the chill water so that this is maintained 1 degree above dew point. Same thing, we charge a slab at night. In the morning it's nice and cool. These systems, radiant cooling, are very, very comfortable. They are very quiet, so there's no noise generated. They're a little expensive, but they're the gold standard for comfort. So a typical control sequence schedule: the system shall be enabled and disabled based upon an occupancy schedule, whatever that is for the space. System pumps: start the lead zone system pump 12 hours prior to occupancy when in occupied mode, so that the slab will be at temperature set point prior to occupancy. If after 5 minutes the zone hot water temperature pump status point indicates no flow, then send a pump alarm failure. So this 12 hours right here can be reset using an optimal start. So if it only takes 2 hours to get to temperature, then you wouldn't want to start at 12 hours, you start at 2 hours. The heating control. During the charge period for heating, run until the slab rises to 78 degrees. During the heating control, during the charge period for heating, run until the slab raises to 78 degree set points or occupancy occurs. During occupancy, start the zone pump if the room temperature is less than 2 degrees below set point for more than 5 minutes. Run until the room temperature is 2 degrees above set point for more than 5 minutes. So it tells you, and a lot of times we'll actually have slab sensors to tell what the sensor of the slab is, because the temperature of the slab and temperature of the air is slightly different. But we can do that, and that's how you run radiant heating and radiant cooling. Cooling control. During the charge period for cooling, run until the slab temperature reaches 72 degrees set point or occupancy occurs. During occupancy, start the zone pump if the room temperature rises above set point for more than 2 degrees for more than 5 minutes. Run until the room temperature is at set point for more than 5 minutes. Every 2 minutes, calculate the room dew point temperature from the room temperature and humidity sensor. Reset the zone chill water supply temperature set point to the dew point temperature plus 1 degree. Reset range will be limited from 55 to 68 degrees. So basically that's how we're setting up the cooling. Typical control sequence monitor points and trend alarms for radiant is monitor all temperature and humidity sensors. If the zone hot water supply temperature is above or below set point by more than 5 degrees for more than 15 minutes, send a level 3 trouble alarm. Now, your trouble alarm level, a level 1 alarm is a life protection issue. It needs to be taken care of immediately. It needs to have high volume alarms. It needs to know, everybody know. A level 2 is a alarm that requires an operator to get up out of his chair and go do something now. So it's an alarm that's going to hurt. It's going to cause problems in the system. It's going to cause comfort problems. We need to deal with it. Alarm 3 is an operator needs to be aware of it, but it's not critical. He doesn't need to take care of it right this moment. He just needs to be aware of it, that he's got a problem going on he needs to deal with. And so that's the level of alarms. If the zone chill water supply temperature is above set point for more than 5 degrees for more than 15 minutes or below set point for more than 1 degree for more than 15 minutes, send a level 3 trouble alarm. Same thing. If we're out of these temperature set points, then we need to know that, but it's not super critical. Alarm all equipment run failures at level 2. So if you lose a pump, then it's a level 2. You got to get up out of the chair. Data trend hot water supply and hot water return and chill water supply and chill water return temperatures continuously with an interval of 15 minutes. So what it means that there's a data trend file within the computer that's been trending these temperatures forever at 15-minute intervals. Now 15 minutes is not very close. You can't do real fully diagnostics with 15 minutes, but you can tell what's been going on. And if you watch those over time, you bring it up and look at a certain window of time, you can see what's going on with your systems. Data trend the room temperature and humidity continuously with an interval of 15 minutes. Same kind of problem. We're going to look at the rooms. Data log run time of all motors and equipment resettable by operators for maintenance. So we're going to watch the pumps so the operators know what's going on. And that's radiant heating and cooling. Constant volume water systems. And constant volume water systems have a boiler or maybe 2 boilers for the heat source, a regular pump, system pump, and a standby pump to give standby in case one fails. Remember, this is a single point of failure. If one pump fails, and there's no water in the system, nothing works. So we need to have some redundancy here. So what happens here is the pumps get the water back from the coils, pump through the boiler, heats the water, sends the water out to the field, and you notice these have 3-way valves so that they're not variable flow, they're constant flow. And so the pumps are starters, not VFDs. Here's the point list. DO1 is a pump 1 start stop. DO2 is a pump 2 start stop. DO3 is a boiler enable disable because the boiler has its own internal controls and will maintain its own temperature. Analog output is a hot water temperature set point. So we're going to be able to take the hot water temperature, and this boiler can stage itself, its fire control, to maintain that temperature. DI1, digital input 1, is the P1 status, these current switches. P2 is a current switch to tell if it's running. P3 is a boiler alarm which comes out of the boiler panel. Analog inputs would be A1 would be the hot water supply temperature, A2 would be hot water return temperature, and A3 would be boiler status. It could be the fire rate, or it might be an alarm. And then we have an outside air temp and outside air humidity. And these are normally global points, but they come in normally to this panel and are distributed to the air handlers if they need it. And that's the point list for a simple hot water system. So the system sequence is formed. First is schedule. The system should be enabled, disabled based upon an occupancy schedule of the space. Pump lead lag. So lead lag status of all pumps should be based upon operator selection or rotated automatically every 7 days. If any pump fails during operation, it should be locked out of rotation and repaired and placed back into rotation and scheduled by an operator. So basically, if a pump fails, it will get an alarm, and the operator, it automatically switches to the backup pump, but it won't go back to this other pump that failed until an operator has fixed it and put it back into the schedule and says it's ready to run. System pumps. That's these pumps here. They'll start the lead pump when in the occupied mode. If after 5 minutes the lead pump current switch status point indicates no flow, then start the lag pump and alarm a lead pump failure. Once the lag pump starts and the flow is confirmed, reset the failed base pump to automatic operation unless it's locked out by operators, and it should be locked out if it's not been fixed. Okay, the typical heating sequence. The hot water supply temperature set point should be 140 degrees. The boiler internal temperature control shall control the boiler leaving water temperature set point. And we've determined that this boiler is going to have a 4-degree span on its temperature, so it'll go from 138 to 142 between minimum and maximum fire rate, maintaining 140. Now this boiler also has a minimum set point of 130 degrees. So at no condition should the set point be below 130, because this is a water tube boiler. If it gets below that, the tubes may rust, damaging the boiler. So they want it between 130 and 180 is what we're going to have here. Okay, so this is the temperature reset control for the hot water system. If the system pump flow is confirmed, then reset the system temperature set point by using a trim and respond control logic loop every 3 minutes. For each coil control valve that are greater than 99% open for more than 3 minutes, send a 3 temperature change request. For each control valve that is greater than 97% open for more than 3 minutes, send 2 change requests. For any control valve that is greater than 95% open for more than 3 minutes, send 1 change request. For any control valve that is less than 95%, send 0 change request. Reset change shall be from 130 to 180. Remember that 130 is the temperature of the boiler, minimum temperature of the boiler. So here is a hot water supply temperature reset loop parameters. These are the parameters that the programmer needs to use to make this logic work. So it really works well once a programmer programs a framework for this, and then all he has to do is, for every other sequence, he can just change the parameters and it locks right in. So this parameter loop has all the things that are important to this control reset loop. 1, the set point is 140 degrees. The set point minimum is 130 degrees, and the set point maximum is 180 degrees. Now these are all designed to be input, and you can make them anything you want as long as you don't go against the boiler manufacturer's minimum requirements and the maximum requirement of your system. I mean, you could have made the set point 130 degrees to start with, but you can't make it below 130 because all the water goes to the boiler. So then we have temperature difference is the times delay is what it is. TD is time delay, and it's 6 minutes. So what happens is whenever this starts and you start the sequence, it's going to wait 6 minutes or 2 cycles before it does anything. So in other words, when it starts, you may have a zone that's way up, it's 100% open, but you're not going to send anything for the next 2 cycles. So you get to the 3rd cycle, then you'll send these requests. So that's a time interval, and of course that's adjustable. And then you have T, which is the time interval, which is 3 minutes. Like I said, we selected that 5 minutes gets to be a little long. In other words, because your reaction time gets really long if you have a wide variance. 2 minutes is a little short, so I like 3 minutes. It's a nice deal. I've used 5 minutes for years. Got in trouble a few times because it takes too long. R is a change request. How many change requests has the system received? And the action to do these is this. If the reset change requests are greater than the ignored request, in other words, so if it's greater than 3, because you're going to ignore the first 3, then the formula is the R minus IR, so it's the actual request minus the IR times that value times the value of this. So let's say you have 8. You have 8 requests that have all stacked up in this 3 minutes. So you're going to ignore 3. So now you come up with 5. So then what you do is you take 5 times 1, right? Because right now we have res is 1, positive 1. So then you would raise it. You could raise it. You have 5, so it'd be 5 degrees. But you've set a maximum raise per 3-minute interval of 3. So even though you have 5 or 8 or 10 or 20, it's going to do 3 degrees maximum. And then this one here is the trim when you don't have any positive request, and then you will start subtracting. So the minute you don't have any, then you will let it go down. So this is the subtracting, or the trim is -4. So you can see it can go up by +3, but it can come down by -4. So it can come down faster than it goes up. And there's a reason for that. We'll show you that in a minute. So that's the formula for that. If the requests are equal to your ignored request, so in other words, if they're equal to or less than 3, then you go straight to trim. And then trim is the -4. So the notes are the reset action increases energy usage, and the trim always lowers energy usage. 2, initial settings to 10% of total connected zones. Add to balance responsiveness to demand fewer ignores versus energy efficiency more ignores. And that's this ignored request. So what they recommend is you pick a number that's equal to about 10% of the connected load. So we have 30 coils. So then I pick 3, about 10% of the 30 coils. Now you could use more or less. If you raise this, then this is going to get less responsive. It'll go down in its responsive. If you put 1, the responsiveness will go up, but also that drives the loop a little bit crazy. So you need some kind of reset in there, or some responsiveness in there. So basically, in note 3, the tolerance for limits or time is 0.05 seconds, temperature is 0.1 degree, and speed is 0.5% or 3 hertz. So that is the accuracy response that we're expecting within these reset sequences. So this is the parameters to make this all work. And I always generate a chart, and what the reason for this is trying to determine what is the time. If you start at your set point of 130 degrees, 140 degrees, and it's super cold outside, so you start getting requests, it's going to wait the 6 minutes, right? And then it's going to wait 6 minutes, and then it's going to search period, and it's got all kinds of requests, and it's going to go up to maximum. And what I'm trying to determine is how long does it take to get where we need to go. So in this one, it's 39 minutes. Which is not terrible. I mean, if you're trying to get from 140 degrees, not doing your job, to get to 180 degrees, 39 minutes is tolerable. What is not tolerable is probably an hour. An hour is going to get a lot of grumpy people, probably. So 30 minutes, 39 minutes, 40 minutes might even be doable. We don't need 5 or 10 minutes. We don't need that kind of response. So I'm just making sure within a realm. Now, the reason I do this is I have done years ago when I was fighting all these sequence issues. I set up one I thought would be really cool. Got out there and tested it. It took 2 hours to get to this point. I said, okay, that won't work. Now, the original sequences I did not have all this variance to be able to prioritize the worst cases. It was typical for all of them, and it just didn't work well. So this works much, much better. So once it gets to this 180 degrees, now we start getting, if we start getting negative sequences, if not, it'll just stay up there until the loads are all satisfied, and then when it starts coming down, it comes down at 4, and it takes 36 minutes to get back down to 130 degrees. So these are all reasonable amount of times, and that's all I'm trying to check here. This is just where I put in requests randomly up here and see how it filters out, and I use those formulas from here to test what the actual up and down will be in this sequence. So these work fine, and this sequence would be acceptable. Trend points for alarms: monitor all temperature sensors. If the hot water supply temperature is above or below set point by more than 5 degrees for more than 15 minutes, sends a level 3 trouble alarm. Alarm on equipment fan failure as a level 2 alarm. Data trend hot water supply, hot water return temperature continuously with an interval of 15 minutes. Data trend the outside air temperature humidity with an interval of 15 minutes. Data log runtime of all motors and equipment resettable by operators for maintenance. So now, variable temperature hot water systems. Okay, so this is a system that's designed to have a wide range of variable temperature. The other one was a standard constant volume, and we were resetting between the boiler, your set point, and the boiler minimum temperature. Well, this one will take it all the way down to another temperature. So this is similar to what we've seen before. This is a variable temperature, but you see it's got more components up here. And what it's got is it has one boiler, maybe two boilers, and there's a primary pump on each boiler. So each boiler has its own primary pump, and it's connected with a loop. So if this water is flowing less water, this primary pump will pump like this. If these are flowing more water than this, then they pump like this. And this is a decoupler. So now there is another item here. This is to change the temperature. So if this is running, say, 140 degrees, and we need 100 degrees, then it will begin to mix this water right here like this. And so as this heats out, it lowers this temperature, and it only takes what it needs when it's bypassing that direction. So this is a hot water bypass, cold water bypass, and it allows us to do the temperature. So here's the points for the system. D01 is the pump 1 start. D2 is a pump 2 start. D3 is a boiler isolation valve. D5 is a primary P3 stop. Stop of the primary pump. This is primary, these are secondaries. And D07 is boiler enable disable. Analog outputs: A01 is a boiler hot water temperature set point. A02 is a bypass valve modulation. So we're going to modulate these bypass valves on temperature reset. Digital inputs: digital 1 is a P1 alarm, D2 is P2 alarm, D3 is P3 status, primary pump status, and DI4, that should be 4, is boiler alarm. Analog inputs: A1, hot water supply temperature of the secondary. A2 is secondary hot water return. A3 is a primary hot water temperature. AI4 is a primary hot water return. A5 is a boiler status fire rate. A6 is outside air. I7 is outside air humidity. And that's a point list for a variable temperature system. So, schedule our sequence. The system should be enabled, disabled based upon an occupancy schedule. The pump lead lag selection, lead lag status of all pumps should be based upon operator selection or rotated automatically every 7 days. If any pump fails during operation, it shall be locked out of rotation until repaired and placed back in the rotation schedule by an operator. It's the same as all pumps. System pump: start the lead pump system when in the occupied mode. If after 5 minutes the lead pump flow switch says no flow, then start the lag pump and alarm a pump failure, just like all the other systems. So this is occupied heating control. This starting and secondary hot water supply temperature set point during occupied mode should be 140 degrees. The boiler internal temperature control shall control the boiler leaving primary water to be secondary temperature set point. If the primary hot water supply temperature is 5 degrees less than set point for more than 15 minutes, start the lead boiler primary pump. If after 5 minutes the pump current switch status point indicates no flow, the alarm primary pump failure and enable the lag boiler, if you have a lag boiler, and lag the primary pump. When flow is verified, enable the boiler control. Reset the secondary temperature set point by the following reset sequence. unoccupied heating control. If the unoccupied mode shall be at 90-degree set point. If more than 3 net reset requests received during the unoccupied mode, start the secondary lead pump and enable the lead boiler and primary pump. Reset the secondary temperature set point by the following reset sequence below. If the secondary hot water supply temperature set point is at minimum for more than 30 minutes, stop the pump and enable the boiler. Okay, now here's the reset sequence for that, and we're going to go through and read all this, but this is the somewhat of a confusing diagram, but it is how this boiler is actually going to do that. So here's the minimum boiler temperature, 130 degrees. Here's our set point, and here's the maximum. But this is the boiler, so the boiler is going to go between here and here, and this is the system. It's going to go 180 clear down to 90. So now, right now, I have a reset sequence, different occupied and unoccupied, and it changes the set point from 140 to 90 degrees for nighttime. But this can also happen during the day. So if you have a nice autumn day and we need a little warmth, but not 140 degrees or 130 degrees, we need 90 degrees. That's what this system will do. Whereas the system we looked at before would not go below this 130, which then would have maybe a little bit of energy loss because we have hot water running through all the lines and we're not using much because it's very hot. When we have lower temperature, we have less energy loss, and we get closer to the temperature they need in the space. So here's the sequence. Reset the system hot water supply temperature set point by using a trim and respond control logic loop every 3 minutes. If any coil control valve is greater than 99% open for more than 6 minutes, send 3 change requests. If any control valve is greater than 97% for more than 3 minutes, send 2 change requests. If any control valve is greater than 95% for more than 3 minutes, send 1 change request. If any control valve is less than 95%, send 0 change request. Reset range shall be for the hot water secondary system should be 90 to 180 degrees. Reset range for the hot water primary system should be 130 to 180. 130 is a boiler minimum. The secondary hot water supply temperature set point should mix water from the primary to the secondary to provide 90 degrees to 130 degree temperature control. From 130 to 180, the primary set point should follow the secondary set point. So what that's saying is the hot water loop, the primary loop, it has a minimum set point of 130, but our set point is 140. Now, if it needs higher than that, then we will reset the boiler temperature up to 180 degrees, wherever it needs to be. But this one here, below 130 degrees, it's mixing water, and it's mixing water up here through this temperature loop. So it's mixing water to lower this temperature. And that's the kind of sequence. Now, it's the same thing. Here is the hot water parameters, which is exactly the same as the last one. 140 set point, minimum 130, maximum 180, except the minimum now is 90. And so the delay time is 6 minutes, interval time is 3 minutes, ignored request is still 3, and the reset is 1, positive 1, reset max is positive 3, and reset trim is minus 4. And the conditions are the same as we talked about the last one. And of course, when I built the chart, this is what it looks like. So we're starting here at 140. And we're taking 39 minutes to get up to temperature, just like the last one, with I'm fooling around with the points up here. But now we need to go down. So it takes now to go down to minimum, it takes a little longer. It takes 66 minutes to get down to that 90 degrees. It will keep going down to 90 degrees. So now remember that these are not real world. This is just the maximum it can do. In reality, these temperatures will, bounce around because it'll get greater or less or greater, and it will go up and down. So this is the way to show that these will actually work and the sequences work. So these are pretty simple when it's only one reset variable. But when we get to two resets off the same reset request, it gets trickier, and that's what we'll do on the next one. This is variable temperature hot water systems monitor alarms. Monitor all temperature sensors if the primary hot water supply temperature is above or below set point for more than 5 degrees for more than 50 minutes. Send a level 3 trouble alarm. Alarm all equipment run failure to a level 2 alarm. Data trend hot water supply and hot water return temperature contingency with an interval of 15 minutes. Data trend outside air and humidity temperature with an interval of 15 minutes. Data log runtime of all motors and equipment enabled by operators for maintenance. Now there's more you can do, but this is what they actually need. More than this they may want, but may not, but they don't need it to actually operate the plant. All right, so this is variable temperature and variable flow. So there would be, in my opinion, this system right here, variable temperature only, I don't see a need for it because this costs almost exactly the same to build as this system. And this system has both variable flow and variable temperature to the space. So it has a decoupler for the primary loop. It has a temperature decoupler for the temperature to the space. So this is, to me, is the preferred system. It's a little bit more difficult to program, but basically to get this results, you've already spent the money, so I don't know why you wouldn't do this. So here's the points. Digital output 1 is a P1 secondary, D2 is a secondary P2, D3 is a boiler isolation valve, number 1, DO4 is boiler 2 isolation valve, DO5 is a starter for the primary first primary boiler primary pump. D6 is the second boiler primary pump. 7 is boiler 1 enable disable, and boiler 8 is boiler 2 enable disable. Analog outputs, AO1 is hot water temperature set point for boiler 1. AO2 is for boiler 2. AO3 is the secondary P1 speed. A4 is the secondary P2 speed. AO5 is a hot water system bypass valve. This bypass valve again. Digital inputs, DO1 is a P1 alarm coming off this VFD. D2 is a P alarm coming off this VFD. DI3 is primary pump current switch, and DI4 is the second boiler primary current switch, because these are not VFDs. These are constant volume. These boilers are constant volume. These are variable volume. And DI3 is a boiler 1 alarm. DI4 is boiler 2 alarm. Analog inputs, AO1 is secondary hot water temperature. Supply temperature, AO2 is secondary return temperature. AI3 is a primary hot water supply temperature. AI4 is a primary hot water return temperature. AI5 is a secondary P1 hertz. AI6 is a secondary P2 hertz. AI7 is a boiler status fire rate. AI8 is the second boiler fire rate. AI9 is a secondary DP sensor. So here's something new. We have a differential pressure sensor up here running these pumps. That's new. And then AI10 and AI11 is outside air temperature and outside air humidity. So similar to the others, a few more points. We know we have an extra boiler, so we added some points to it. Here's the control sequence. Schedule. The system shall be enabled, disabled based upon an occupancy schedule. Lead lag pump set of all pumps shall be based upon operator selection, are rotated automatically every 7 days. If any pump fails during operation, it shall be locked out for rotation until repaired and replaced back into the rotation by an operator. Secondary system pumps. Start the lead system pump when in the occupied mode. If after 5 minutes the lead pump current switch indicates no flow, then start the lag pump and alarm the lead pump failure. These are actually the primary pumps. Secondary pumps are the same, except they're VFDs. Occupied heating controls. Start the secondary hot water supply temperature set point during occupied mode should be 140 degrees. The boiler and terminal temperature shall control the boiler leaving primary water to the secondary temperature set point. The primary hot water supply temperature is 5 degrees less than the set point for more than 15 minutes. Start the lead boiler primary pump. If after 5 minutes the pump current switch status point indicates no flow, then alarm primary pump failure and enable the lag boiler and lag primary pump. When flow is verified, enable the boiler fire control. Reset the secondary temperature set point by the following reset sequences. Now the unoccupied is exactly the same, except the set point's 90 degrees instead of 140 degrees. All right, typical control sequence. Variable temperature, variable flow reset control. The reset sequence shall reset both the hot water supply temperature and the hot water supply differential pressure using the following trim and respond logic loop. The reset sequence shall be constrained by the hot water supply temperature reset based upon the hot water supply differential pressure speed to provide hot water temperature priority. The secondary hot water temperature shall start at 140 degrees set point, and the hot water supply differential pressure shall start at 12 Hertz. With all reset requests received applied to the hot water differential pressure set point, the hot water DP resets up to meet the demand load. Once the pump speed resets to 60 Hertz, the pump speed shall be locked at this point, and all reset requests shall be applied to the hot water supply temperature set point when the hot water supply temperature resets back to minimum 130 degrees. All reset requests should be applied to the hot water DP set point until pump speed reaches minimum speed of 12 Hertz. It continues at this level if all reset requests are applied to the secondary hot water temperature set point. If both the hot water supply temperature and the hot water supply DP are at a minimum for more than 30 minutes, disable the boiler and stop the system pump. All right, so this is kind of wordy, and we're going to kind of get into what this actually says. So what we're doing, here's the example of what we're trying to do. So here is the start option, and here is the maximum. Here are the temperatures of the system. Here are the hertz of the motor. So here's the pump. So we start the pump, and the change requests are applied only to the pump until it gets up to maximum speed. And this is at minimum temperature down here. This is at 140 degrees for the boiler. So what we're going to do is we're going to try to make 140 degrees meet all the requirements of the load by increasing the pump. And the reason for this is the pump is much less energy usage than the boiler. The boiler takes more energy, more cost to make heat than this pump does for flow. So we want it to go up to maximum flow. Once it reaches that point, then we let the reset request apply to the water temperature, and they reset up to maximum. So here, 180 degrees. And that's how it works. Now on the opposite side, it's the same. So what happens, we're up here, we're right at this point right here, and as we start to get negative change requests that we want it to go down, then we leave the pump high and we let the system set point go down to this point right here, that 130 degrees. So at 130 degrees now, we'll let the resets do both. So now it's going to start lowering the pump, and it's going to start continue to lower the temperature. Once the pump's down to 12 Hertz, then it will continue this, it will continue this down to minimum, which is 90 degrees, and then the pump will go down to 12 Hertz. Once these have both been there for a long time at 12 Hertz, we're going to disable the boiler because it doesn't need any heat. At 90 degrees, it's really low temperature, and you don't want to continue to run the pump for no benefit, so we would then turn it off and then not do something until we get into a start sequence again. So here's the actual variable flow reset sequence. Every 3 minutes, evaluate the system reset request. If any coil control valve is greater than 99% open for more than 3 minutes. Now on the last video, I actually made a mistake here and I said 6 minutes. And when I made this, I was thinking about the delay time, which I have a delay of 6 minutes. But this should be three, because we don't do any of these until after the 6 minutes. So if the control valve is more than 90% open, then you send 3 requests every 3 minutes, send 3 change requests. If any control valve is greater than 97% open for more than 3 minutes, send 2 change requests. If any control valve is greater than 95% more than 3 minutes, send 2 change requests. If any control valve is less than 95%, then send 0 change requests. Reset range from the hot water supply secondary system shall be from 90 to 180 degrees. Reset range for the hot water supply primary system shall be from 130 to 180 degrees. 130 is the boiler minimum. The secondary hot water supply set point shall mix water from the primary to the secondary to provide 90 degree to 130 degrees temperature control. From 130 to 180, the primary boiler set point shall follow the secondary set point. And this is what we talked about before, where this is the boiler system. This is its minimum of 130 degrees. And if this system needs hotter than 140 degrees, then this system will reset up to provide that hotter. If this needs colder water, like it needs 100-degree water, then it will mix water through the temperature loop to lower the water temperature. The boiler is at 130-degree set point, and this will allow colder water to the field. All right, here's that standard hot water temperature reset loop parameters. And it's the same as the others. 140 degree is our set point, 130 is minimum, 180 is maximum. Basically, this one goes down to 90 though, so it can go down to 90 for that. Reset temperature are plus 1, plus 3, minus 4, so it's the same as the other one, and the reset criteria is the same. Then we have a new one now, it's hot water pressure reset loop, and we got a hot water differential pressure set point is 10 psi, minimum hot water is 8 psi, and maximum is 18 psi. So we allow our system to run between it. Now these numbers are originally established, the maximums are established during balance. And it may, if it's 20 psi, then that would be maximum. At 15 psi, then you would change these accordingly. Delay time is 6 minutes, that's the start time. Internal time interval is 3 minutes. The ignored requests are 3, and again, we're using the 10%. We have 30 coils, so we're going to say 3 is the number. And of course, these are all changeable by you, so you can change them to customize where you want the priority to be in your system. Now, the set point resets. The loop action makes higher differential pressure, so a reset uses more energy. A trim uses less energy, and so right now we're at 0.25, a quarter of a psi, and maximum is 2 psi. We'll raise it 2 psi to maximum. So if we have more than, we're raising 2 psi, so we'd have to have 8 requests to get to 2, and we're 1.5 psi in the negative, so we'll go down fairly quickly. And again, it's the same as everything else. So if the requests are less than I, which is the ignored request, then R equals minus IR times res times the variable. So basically, you could be, if you get 6 requests, and you could, because if you have one that's 90%, that's 3 requests. You have another one that's at 98, that's 2 requests, so it could get to be 5 right quick. So this is trimming it off of what are we going to do in that system. So these are both version out. How we actually keep this from not conflicting with each other, here's the way this works. So here is the temperature profile. So here is the temperature starting at 140 degrees. Yeah, 140. And you can see it comes along, it waits the 6 minutes, and then it get a change request. But it doesn't, here's the 6 minutes. So it's 3, 6 right here. So it gets a change request started right here. And our pump starts down here at its minimum, which is 8 hertz. And it starts, and so we apply the first reset request to the pump. We always do the pump first. And it begins to reset until it resets up to maximum, which is 18 psi. And then the next request is actually, the very next request is actually now set to the temperature. So we're still getting up request in here, so it begins to increase the temperature until it gets to maximum. And then if we get negative request, it starts doing negative requests till it gets down to minimum, and then it starts lowering the pump speed. And that way we're able to lock these together so the physics doesn't mess it up. So basically we're running the pump up first, so we're trying to do the maximum load with this boiler at set point at 140 degrees. We don't want to go up, we want to stay at 140, but when the pump is up all the way in flow, then it still has requests. We let the boiler start to heat up the water. When the water's at maximum and the pump's at maximum, then we still apply the negative resets, the 0 reset request, to the hot water till it gets down to minimum, and then we let it lower the pump. So that this keeps us from doing any kind of wind-up. And wind-up is a mystery that can just drive you absolutely crazy. If you don't lock these together, you don't have some mechanism in your sequence to make sure that the pump can go to minimum and the hot water go to maximum, which is possible, or vice versa, or both one way or the other, it can drive you absolutely crazy. But so this actually prevents all that. These sequences give you good control over how quick you move, and this one, of course, is the temperature. The pump goes up. It's 27 minutes to go up, and it's for the hot water to start. It goes 39 minutes, and down is 36 minutes. So it's the whole thing. It can go from maximum to minimum in 2 hours, which is pretty quick, actually. You know, if you don't think that's quick enough, then change your interval to 2 minutes. You could do it, or you could make your resets more aggressive. Either way, but that's kind of how you do this. And this will work, and these work well once you get them figured out how to set them up. Typical control sequence with the monitor points for this, and monitor all temperature sensors of the hot water supply temperatures above or below set point for more than 5 degrees for more than 15 minutes into level 3 alarm. Alarm equipment fan failure at level 2 alarm. Fan failure. All equipment run failure. Run trend hot water supply return continuously for 15 minutes. Data trend outside air humidity 15 minutes. Data log run time of all motors resettable by operators for maintenance. Data log a running total of requests per week generated by each zone to identify zones that are driving the reset logic. So if you do a data log on the running total of the requests per week, you'll tell which one of those boxes is actually, if you get one that's generating requests every 3 minutes all the time, that box has got that coil's got a problem, and you have to go figure out what's going on. So that's a very easy way to do it. I used to do it by doing a report, but this is the same thing. It's a data log, and it will give you a report to do that. So now we're going to talk about hydronic system set point change suppression. When we do these automatic resets, the way we're doing it with reset requests, we need to think about suppression, and here's why. I'll tell you what's going on here. So anytime a water temperature set point is reset greater or equal to 1 degree, start a suppression timer that prevents more reset requests or set point alarms for 3 time intervals. If after that the reset condition remains the same or is greater, extend the suppression timer another 3 time intervals. And if after that the reset condition remains the same or is greater, extend the suppression timer another 3 time intervals. Then end the suppression timer. So what this is actually doing is, if you have a water temperature set point and you change that temperature set point by 1.5 degrees or 1 degree, and then the interval goes, and it's at the end of that 3 interval, the system didn't actually fix anything. It didn't actually increase. So now, you didn't change the temperature. You had a set point change, but nothing actually happened. So that now the resets get larger, and the alarm persists. So then it asks for more, and then you wait 3 more intervals or another interval. It doesn't work. It's going to ask for more. So what happens is it keeps asking more and more and more requests, but the system's not responding. So what it'll do, it'll drive your temperature requests all the way to maximum, whatever that is, or minimum, whether your temperature's going up or going down. And that's not what we want to do. That would increase energy proportionally, so we're not doing that. Now, eventually the alarm will trigger, and the operator will figure it's not working, but we don't want to drive these resets completely out of sight because of that. And it may not be that it's working. It may be because the mass is so large, it's going to take longer. That's what we're trying to do, is we're trying to get somewhere around 30 minutes of time of suppression of the alarm and suppression of the resets. So then, now this is per set point. So if you have a whole bunch of set points, the others may be doing other things, but this one, for each one, you're going to put this suppression formula in place, and it will help it stay stable. Good. I hope you enjoyed that. I hope it was really helpful to you. This would have helped me if I'd had this 10 years ago. I could have got past some reset sequences that drove me crazy. So I really appreciate you watching. Thanks for watching. Please share these videos with other folks that you think it might be beneficial. I'd appreciate it. Have a great day, and I'll catch you on the next one. Thanks.